Today we're going to learn about the causes and effects of a buoyant force and how to calculate the buoyant force on an object. Okay, so you know when you're in a swimming pool and you can pick up your friend in the swimming pool and she feels lighter than she usually does when in the real world. That's because the water is actually exerting a buoyant force on her. So it's buoying her up. So there's a buoyant force acting on her that actually counteracts the force of gravity. So if you were on the land, you would have to lift up against this force of gravity, but since you're in the water, you have this buoyant force, and she appears, which means her net force is the difference between her gravitational force and the buoyant force. Okay, so she appears to weigh less. So what causes a buoyant force to occur? Well, when you have an object in water, there's a pressure here at the bottom and there's a pressure here at the top. And as you get deeper and deeper into the water, the pressure increases. So there's actually a pressure difference which causes our buoyant force. And it turns out that when you have an object and its volume, so volume, get all of our terms correct. So the volume of this object is the same as the volume of water it displaces. So that will tell us basically how much volume of fluid is displaced. So the volume of our object, once we know the volume of our object, which we can calculate, that would be the volume of the fluid that was displaced. If it's all the way submerged, we're assuming it's all the way submerged at this point. And notice I use the word fluid, and normally we think of this term fluid as just like a liquid, but a fluid is anything that flows. A fluid is anything that flows. So it's air or it's a gas or a liquid. It doesn't have to be water. It's a gas or a liquid. So how do we experience air flowing? Yeah, wind. Wind is air flowing. So air flows, that's how gases flow. It's like a wind. You feel the air flowing out of your air conditioning. So the fluid is any substance that will flow. So gasoline, water, air, helium, whatever the surrounding fluid is. So now we know that the volume of the object is the same as the volume of the fluid that is displaced. So how do we know if something sinks or floats? Okay, remember we had our drawing and we had our object in the fluid. Okay, and we had two forces acting on it. The buoyant force is always going to work up. It's always going to push the object up. And it has to do with that pressure difference between the top and the bottom. Gravity is always going to pull it down. So if our buoyant force is larger than our gravitational force, okay, it's going to go in the direction of the larger force. So that's going to make it rise up and it will float. You've tried to push a balloon or a ball under water and you've noticed it's really hard to do, and then as soon as you let go, it pops right back up. And it pops right back up because this buoyant force here is larger than the weight. Remember, force of gravity, fancy word for weight, okay, is greater than the weight of the object. Now, if it sinks like a rock, okay, a rock has a larger weight than the buoyant force acting on it. So which one of these forces is bigger will tell you, is it going to sink or is it going to float? So how do we calculate the buoyant force? Well, it turns out that that buoyant force is the weight of the displaced fluid. Let's say that again. Buoyant force is the weight of the displaced fluid. So how do we find that weight? Okay, so you know how density, remember density from before, density is mass divided by volume, right? Okay, so if we wanted the mass, that would be our density times our volume, getting volume off the bottom on both sides. Okay, and then how do we go from mass to weight? Remember, to go from mass to weight, we take our weight. So this is our buoyant force now, because it's going to be the weight of the displaced fluid, and it's going to be the mass, which is our density times our volume, times gravity. Okay, so it's very important in this equation. Well, actually, let's express it in Greek terms like we usually do. Okay, the Greek variable for density is the Greek letter rho. See how I wrote that? It's kind of like a P, but it's not a P. Rho G V. So all we did was took here our density and we substituted with the Greek letter rho. Okay, and we rearranged this order. So this is usually how you see the formula written in many places. So that's an important, and this is an important idea. So make sure you get this idea-wise, but this would be the equation to get it. So our buoyant force is the density times gravity times the volume. That's a big V, not a little v, so you don't get it mixed up with velocity. Very important. This density that we're talking about here, this density, is the density of the fluid, because we want the weight of the fluid. So if we wanted the mass of the fluid, we use the density of the fluid and the volume of the fluid. But remember, the volume of the fluid is the same as the volume of the object. So that's easier, but the density, that's really important. So let's write that down. We need to make sure that we use the density of the fluid, okay, when we calculate our buoyant force. So in our lab, what we did is we had a block. Okay, we calculated the volume of the block. Okay, so volume equals length times width times height, not hard. Okay, calculate the volume of the block. And remember that the volume of the block is going to be equal to the volume of the displaced fluid. So if we put this block in water and like push it down so it was completely submerged, our buoyant force is rho GV. Don't forget, there's our equation. So it's going to be the density of water. So the density of water is 1,000 kilograms per cubic meter. Okay, so if you think of a meter by a meter by a meter, that's 1,000 kilograms. Water is very, very, very heavy. So we would put 1,000 in there. If it was in water, if it was in air, we'd put a different density, times gravity, times whatever this volume turned out to be. And that would give us the buoyant force. That's the maximum buoyant force on the block. And it will float as long as the buoyant force is larger than the weight of the object. Okay? When the buoyant force equals the weight of the object, then it's called neutrally buoyant. And this is what fish are. Fish are neutrally buoyant, which means they'll just hover in one spot, and that's why fish can swim through the water. And pufferfish actually swell up. So remember rho GV for our buoyant force? Okay, so a pufferfish will swell up, so its volume is bigger, so the buoyant force is bigger, and that causes them to rise up because now the buoyant force is greater than the force of gravity, and they will pop up and float a little bit. They don't actually go all the way up to the air because then they swell down. But that's one of the ways that fish can regulate, you know, their upward velocity or downward velocity, is they can change their size. Sometimes they swell up, sometimes they don't. Some fish just use their fins to swim, and that's how they get from A to B, and they're just totally neutrally buoyant. But some of them actually change their volume so they can get up and get down. So that's the basics of what you need in order to calculate buoyant force. If you have any questions, please bring them up in class.